So in this segment, we are going to return to our study of the stress, okay? With a reason, because we're going to study the stress, but eventually come back to this notion of stress power. In studying the stress again, we are going to introduce additional definitions, if you will, of the stress, but they are really different stress tensors, okay? So we're going to introduce measures of stress in addition to the Cauchy stress. Okay? Here's the motivation for doing this. Suppose we have a situation where we have a bar, right, a cylindrical bar, and we are going to subject this to a force, okay? And since that force has to be balanced, we have a force at both ends, okay? Let's suppose that in this, so this is omega naught, right? Reference configuration. And let's suppose that the cross-sectional area of the bar here is pi r square, okay? And the length here is capital L, right? We apply the force, and under application of the force, this bar gets elongated, all right, a lot. And it's just my poor drawing that makes it look like it's that's given it a varying cross section and all that. Let's assume that all of that is the same, okay? So it maintains the cross section, the force is the same. But now let's suppose that this has changed to pi little r square, and that this deformed length is little l, okay? And this, of course, is omega sub t, okay? And that's the deformation, right? Okay. Let's suppose that what we have here is an incompressible material such as rubber, okay? Suppose material is incompressible, example, rubber. Here, rubber is pretty much incompressible. All right. Okay. So, well, what happens here is that we are going to have pi r square, L equals pi little r square little l, okay? And therefore, if you look at the ratio of initial to final cross-sectional areas, it is in this ratio of little l to capital L, okay? And the way I've drawn the figure, and as you can imagine, if every time you've played with a rubber band, rubber stretches a lot, so that ratio little l over l can be big, and therefore so can that ratio of areas, right? Could be very much bigger than 1, all right? But now also observe that in this setting, in the setting of the current configuration, the force, because everything is nice and uniaxial, we have that the force F is equal to sigma E1, right, times pi r square. Okay. For this, I need to make sure that my axes are, my bases is lined up properly. That's E1, E2, E3. Okay. All right. Now, what tends to happen is that when we look at the force relative to the current area, we get our Cauchy stress sigma. Okay. However, this relation here tells us that the area has changed tremendously. Okay. So if we may ask ourselves, well, what happens if we were to compare the force with respect to the reference area, right? The area before deformation. Okay. Note that F over pi capital R square would be very much less than F over the current area, okay, which is sigma E1 there. All right. And furthermore, and what we're getting to here is this idea that, well, the area is changing so much, the body is deforming so much that things really look very different between the reference and current configuration. Now, in this particular example, it's not such a big issue because I've shown you a uniaxial deformation case where you can say that, well, I know what the original area is. It's not very difficult for me to measure the final area and so on. So, there's not much difference whether you consider this or that, right? Well, there may be a big difference numerically or in magnitude, but it's possible for us to measure both the radii, right? However, consider a different situation where the body now is not a nice cylinder, and furthermore, the deformation doesn't keep it a cylinder, right? So consider the general cases that we had here. All right, this is rubber, right? And it's deforming. It has to deform, maintaining its volume, right? Because it's incompressible. Okay, the same sort of situation. What you would see is that it could very well get really narrow and stretched out, right? That's omega sub t. Now, if you were an experimentalist, if you were trying to measure the Cauchy stress, it could get a little difficult here, right? Because some of these cross sections, like that one, may be difficult to access in an experiment, right? Right? And furthermore, this thing could be deforming in all kinds of funny shapes. In fact, you don't even know what the orientation of the ideal cross section is inside. Okay? So it becomes difficult in this case, in general, it becomes difficult, at least experimentally, right, to measure sigma, right? Because sigma, remember, is defined in that way, right? If that is your normal n, then we have sigma n equals t, traction. You don't know how that area is oriented on the inside, right? It's therefore difficult for you to say what to say what the traction is, right? In what direction are you measuring the traction? Okay. Whereas if you had access to the reference configuration, right, because you know exactly where you start from the reference configuration, it becomes a little easier for you to measure these sorts of things. Okay. Since the reference configuration is fixed and what you start out with, you can decide where you start with, right? However, you don't know what's going to happen in an experiment. You don't know what kind of shape it's going to finally deform into. That's why you're doing the experiment, and therefore it's often difficult to measure the Cauchy stress. Okay? So this is motivation for another measure of stress where somehow you're referring it back to the reference area. Okay? So what we want is, it is useful to have a stress measure that is based on the reference area. Okay? How may we go about doing this? The way we could go about doing this is the following. So on this body, let's suppose that this is our normal direction n. Okay? And that goes off into this normal n. Okay? That same little elemental area. Okay, so we have n dA here. That area vector goes on to becoming n d little a here. Okay? Let's suppose that we deform this body by applying a traction. Now the important idea here is that since the traction is something we are applying as a boundary condition, we can always control the direction of traction. And in fact, let's suppose that we are indeed doing this, okay? That we are controlling always the direction of the traction vector. So even though this is n here, okay, so that is n, and the traction, okay, I'm going to draw the traction here. I've drawn it off the body because I didn't want to interfere it with didn't want it to interfere with my writing of NDA there. Okay, but it's the same traction applied there. Okay, the critical idea here is that the traction is fixed. Okay, so even though we're deforming the body, even though the body surface is changing, the orientation of the surface is changing, NDA, which had this orientation in the reference configuration, has gone to a different orientation here in the current configuration. Okay, in spite of that, the load by which we are deforming the body, the traction by which we are deforming it, is the same. Okay, so for instance, this is the reference configuration of the body. Okay, the finger, or better still, the arrow here is the traction we are applying on it. Okay, the body deforms, and let's suppose that in addition to just locally deforming, it even moves to some other place in the configuration, right? That the orientation of the traction vector remains the same. That arrow remains the same between here in the reference configuration and there. The orientation remains the same, and the magnitude as well. Okay? All right? So this is the condition that we're considering. Under this situation, we can say now the following, right? What we can say is that, look, in my reference configuration, I have the traction, right? I have the traction which is related in some way to this area vector. Okay, I haven't filled things in. There's something that's going to come in this big space I've left here. Whereas back here, I have T equals something, some other stuff multiplying little n dA. Okay, in both cases, I need to multiply this by dA to get a force. I need more room there. Okay, that's my force. Okay, and just for correctness, let me change this here. Let me use a capital T here because it's reference. A capital T here in the reference configuration and a capital T here. Okay, all right. So here, in the case of the current configuration, we know that the relation is through the Cauchy stress sigma. Okay. Likewise, in the reference configuration, it's got to be through some sort of a transformation, just going by Cauchy's theorem. Let's give it a different symbol P. Okay. What we are requiring is, again, this idea of dead loading. Okay. But, as we did in this example here, it's the force which is the same. Okay? It's the total force which is the same, which means that we have capital T d capital A equals, T d capital A equals little t d little a. Okay? So the force, the external force, on the boundary is fixed, right? Right. So somehow what we're doing to the body from the outside, how we're loading it from the outside is fixed. The body is responding differently. It looks as something in the reference configuration, it looks different in the current configuration. Okay. Okay. So this is what we're asking. Okay. This is the condition we're imposing. So what that implies for us is that P n d capital A equals sigma n d little a. Okay? Now, we've encountered all these objects before except for this new symbol P. Okay? We're going to say more about it in a little bit. Okay, so the way we do it is the following. So we recall Nansen's formula. Okay, which is little n d little a equals j, which is the determinant of the deformation gradient, F inverse transpose, where F of course is the deformation gradient, n d capital A. Okay, what that implies then is that P n d capital A equals sigma, j is a scalar, right? So I can pull it out here. Sigma F inverse transpose n dA. Okay? And by comparison, we see that this new object that we introduced, P, is indeed a stress. It is J sigma, which is the Cauchy stress, F inverse transpose. Okay? So this is a new measure of stress. This is called the first Piola-Kirchhoff stress tensor. Okay. Now, when you look back at just the line before, it should be clear to us that because of the fact that we have this defined in this manner, right? And the force on the right-hand side we said was fixed. Okay? That force is always the same, whether it's always directed in the same way in space, also has the same magnitude. This TD capital A is the same between the reference configuration and the current configuration. Okay? Both of those are equal. TDA is the same in the two configurations, right? So we have TDA equals little t d little a. All right? So what this tells us is that this new stress tensor that we've introduced has force directed in some orientation in space, but the area that it's referring to is on the reference configuration. Okay? It's out here. Okay? All right? So P is thought of as force in space per unit area on the reference configuration. Okay? All right? The relation that we have here, P equals J sigma F inverse transpose. Okay? Let's see what the indices of P are. Okay, so in coordinate notation, we have P here. Let's work things out. J, of course, has no indices because it's a scalar. Sigma has indices I, J. Now, F inverse transpose, right? We write it as F inverse, okay, right? But now F inverse transpose will have indices JJ, okay, all right, and this is here's why. It's basically F transpose, okay, sorry, F inverse here, okay, so we would have F inverse, okay, the indices of F inverse are JJ, right, but then the indices of F inverse transpose are the transpose of this, right, so we flip the indices on this to get here, okay, right, so that's why, right, so I should say, since that's how the indices on F inverse would work out. Okay, so F inverse transpose has indices little j, capital J. Okay, when we work things out, what we see is that P now has indices, which I don't need another equal to sign here. What I see on the left hand side is that the indices on P are little I, capital J. Okay, and it's the fact of these indices that truly remind us that the first index, little I, corresponds to the force, which is directed in space, right? It's a spatial index, so it's little. Okay, the second index J tells us about the area, right? Because that's that index J which is going to get contracted out with the index of the area vector. Okay, and that's why the second index on P is uppercase, reminding us that P is a stress defined per unit reference area. Okay, so current, and that is reference. Okay, all right, and the way this would work out when we put things together would be Pij n capital J dA equals Ti dA. Okay, and in the case of the Cauchy stress, we would have sigma I little j n little j d little a equals T little I dA, right? And these two are equal. Okay, so that's how all the indices work out. Okay, the first Piola-Kirchhoff stress is also called the nominal stress. Okay, yes, I should probably say also called. Right, in the chances are when you studied your perhaps your first or second class in mechanics of materials as undergrads, you were introduced to this idea of the engineering stress, okay, which is a stress defined per unit original area. Well, this is it. Okay, this is the first Piola-Kirchhoff stress, or the nominal stress.